Thank you for introduction. Thank you for coming. I'm Will from University of Chinese Academy of Science. I will do presentation for Haibo from Peking University. This is joint work between Peking University and Penn State. Password-based encryption is a fundamental scheme in many real-world systems of authentication or encryption. We usually use password to unlock a mobile phone or log in some internet service. We also use password for encryption to protect our private data. In these cases, PBE is indispensable. PBE has a fundamental defect. The key is password. As the previous speaker said, it is easy to be cracked. To address this issue, two countermeasures are used. The first one countermeasure is to increase the complexity of encryption. For example, sorting can make attacker do the cracking for each user. Using special password hashing function can directly increase the time complexity, but also increase the legitimate users caused by the same factor. The second countermeasure is to harden passwords with other factors. Some typical factors are fingerprint, iris, smart card, and smartphone. But it needs extra device to read these factors or be a factor. This performs worse than single password on dependability. In addition, if the device factor gets stolen or lost, the encrypted message cannot be recovered. Jules and Ristenpark proposed a novel countermeasure on Eurocrypt 14, named honey encryption. This idea is to generate a decoy message to confuse attackers. This countermeasure does not increase the cost of legitimate users, does not decline on deployability, and significantly improves security. As shown in the right figure, honey encryption uses a distribution transforming encoder to encode the message to a seed, then encrypts the seed. The seed follows a uniform distribution. If an attacker uses an incorrect key to decrypt, she will get a random seed. Decoding the seed, she gets a plausible decoy message. George and Ristenpark proposed an IS-DTE with honey encryption. Here I gave a simple example to show how the IS-DTE works. This example is given in George and Ristenpark's paper. Assuming we have a message of ice cream flavor. The probability of strawberry is a quarter, vanilla a half, and chocolate also a quarter. According to the message distribution, we assign strawberry 1 seed, vanilla 2 seeds, and chocolate 1 seed. When encoding a message, random pick a seed in all seeds of the message. With IS-DTE, a non-uniform message is encoded to a uniform seed. In the opposite direction, decoding a uniform seed yields a non-uniform message. IS-DTE is good enough for simple distributions. For example, uniform distribution and normal distributions. But it is a great challenge to design DTEs for message following intricate distribution. Usually we need a probability model to characterize the message distribution, then design a DTE for the model. We name such DTEs probability model transforming encoders. A PMTE is secure if and only if the decoy message generated by the PMTE are indistinguishable from the real message. This includes two parts. The message distribution and the probability model are indistinguishable, and the model and the PMTE are indistinguishable. Until now, 3 honey encryption applications has been proposed. 2 for password vaults, 1 for genomic data protection. This application designs specific PMTEs for their message. However, the security analysis for existing PMTEs is not comprehensive. In fact, the genomic data research did not consider the difference between the message distribution and the probability model. And the password vault research did not consider the difference between the model and the PMTE. In addition, these PMTEs are designed for specific message distribution or probability models. There is still a lack of generic designing method. These issues on PMTE study hinder the widespread use of HE. We propose two kinds of attacks. Distribution difference attack exploits the difference between the message distribution and the probability model. Encoding attack exploits the difference between the probability model. They all achieve high accuracy to distinguish real and decoy messages. We also propose a generic designing method for PMTEs and to prove that our IS-PMTE are indistinguishable from the corresponding probability models. This means our IS-PMTEs resist encoding attacks. Using our method for password vaults, and no encoding attacks achieve more than 52 accuracy. It is slightly better than the expected value of 50%. Before expanding our attacks, we first describe the attacker model. For honey encryption, we consider the attacker has stolen the storage file, for example, the ciphertext. She knows the PBE and the DTE. She can enumerate all keys offline. And she maybe knows some statistics about the real message. Our encoding attacks does not need this. She can perform a certain number of online verification. And this is for password vault. With above ability, attackers want to distinguish the real message from a large number of decoy messages. What attackers will do with the stolen ciphertext? She first enumerates all keys to decrypt the ciphertext and gets a large number of messages. Only one of the messages is real. For password vaults, she can sort them by some means and verify them online. For genomic data, she can only pick one offline. We use a weight function to formalize the sorting means. An attacker sorts these messages in this decreasing order of their weights. Usually the weight PM reflects the probability that M is real. In this paper, we only consider the security of PMTEs. In fact, the strength of passwords also influence the security of honey encryption. Since this has been studied by many researchers, we do not consider in this paper. We use the same security metrics as previous work. The rank of the real message is in relative form. For example, in 1,000 decoy message, 30 rank in front of the real one, then the rank of the real one is 0.3. We use the rank cumulative distribution function, the average rank and the accuracy as our security metrics. The accuracy is the probability that the attacker distinguishes the real message between one real and one decoy. For example, the real one rank in front of the decoy one. An interesting thing is the sum of the average rank and accuracy is equal to 1. This is not noticed by previous work. Now we introduce our work. The first one is a simple distribution difference attack against the GenoGuard. The genomic data protected by GenoGuard is an individual single nucleotide variant sequence. This sequence is represented by a string with 0, 1, 2 alphabet. We use a small real dataset published with the code GenoGuard on GitHub. It includes 165 individual SVM sequences of length 1000. The decoy data can be generated by decoding random seeds with a PMTE. Our attack first uses a principal component analysis to reduce the dimensionality from 1000 to 10, then uses a support vector machine to classify the sequence. We randomly pick half of the real sequence and generate the same number of decoy sequences for training. First, train PCA model and then train the SVM. After training, we use the rest real sequence for test. We generate 999 decoy sequences for each real one to calculate the ranks. Other metrics, the weight for sequence is the probability that this sequence is real. The probability is estimated by SVM after dimension reduction with the PCA. The right table and figure shows the experimental results. The combination model is recommended by GenoGuard. It performs best. But our attack still achieves 76% accuracy. In addition, 47% individuals' real sequence rank first. These users cannot get security improvement by using GenoGuard compared with traditional PBE. Our another work is attacking against the password vault schemes. We now introduce the password vault briefly. A password vault stores one user's multiple passwords on different websites or services. These passwords are usually weak and similar. Here we take NoCrack as an example to describe our attacks. NoCrack uses PCFG model to characterize the single password distribution. For example, this model treats password 1 as a combination of two parts. One is an English word password. The other is digital 1. Therefore, it can be generated by these three rules. NoCrack uses subgrammar to characterize the password similarity. For example, the vault contains two passwords, password and password 1. They share the same part and the same rule. Then the subgrammar of the vault contains these four rules. To enable a vault, NoCrack first parses its subgrammar and encodes the subgrammar. Then encodes each password in the vault based on the subgrammar. And finally, concatenates all seeds and outputs a concatenation as the seed of the vault. It is an opposite direction to decode a seed. First, decode the subgrammar, then decode the password based on the subgrammar. Note that the subgrammar for a real vault is passed from the vault, but the subgrammar for a decoy vault is generated randomly. This leads to the following phenomenon. There definitely exist no unused rules in subgrammar for real vaults, but may exist for decoy vaults. We name this feature UR. There definitely exists no duplicate rules in subgrammar for real vaults, but may exist for decoy vaults. We name this feature DR. Based on these two features, we can exclude around half of decoy vaults and achieve more than 70% accuracy. To save time, we don't go into details here. You can read our paper. These features attacks do not need any statistics about the real distribution and only exploit the DTE PMTE. We name such attacks the encoding attacks. The distribution difference attack seems oblivious, but the encoding attacks seems a little tricky. Why these password vaults cannot resist the encoding attacks? Is there other features? What is the principle for encoding attacks? To answer these questions, we first formalize the probability model into a unified form. Intuitively, A probability model designs a series of generating rules to assign messages probabilities. The probability of a message is the probability it is generated by the rule. Based on this idea, we give a generic conceptual probability model in formal definition. It is natural to formalize a probability model to a GPM. For PCFG model, a generating rule is a production rule. A generating sequence I is a derivation of a string. Here we only consider leftmost derivations. Other derivations can be converted to leftmost derivations equivalently. The conditional probability of a rule only depends on itself. This is PCFG model. For subgrammar, we give an example for explanation. The first rule of the subgrammar is S is equal to 2. This rule represents there are two rules with the left-hand side S in subgrammar. Immediately after, there are two rules, S goes to D, S goes to W. The following rules have the similar form. This sequence is also leftmost, which means expanding the leftmost unexpanded variable first. Other models also can be formalized naturally. For Markov model, a generating rule is a character, a sequence is a string. We use a generating graph to represent a GPM visually. This graph is a direct acyclic graph with a single source. The edge represents a generating rule. A sink represents a message. A path from the source to sink represents a generating sequence called a generating path. The right figure is a generating graph of PCFG model. There are two generating paths for password, the red dashed one and the blue dashed one. Therefore, the model is ambiguous. With the generating graph, the defects of password vaults PMTE becomes oblivious. The corresponding probability models are ambiguous, but the PMTEs only choose one deterministic path when encoding. For example, only choosing the red dashed one for encoding. Therefore, a seed of another path is definitely a decoy seed. According to this finding, we propose two generic encoding attacks. Weak encoding attack directly excludes these seeds whose path cannot be chosen when encoding. This encoding attack seems oblivious, unlike previous feature attacks, which need to be specific analysis on specific PMTEs. Strong encoding attacks sort the rest seed by the reciprocal of PIS. Here, IS is the generating sequence of the seed. In the figure, the purple line corresponds to the strong encoding attack. It performs well, achieving more than 98% accuracy. Since the principle of encoding attacks becomes oblivious, the countermeasure is also oblivious. Choose one generating sequence randomly when encoding. Based on the notion of GPM, we give a generic method for transforming arbitrary GPMs to PMTEs. Firstly, we introduce the notion of conditional DTEs. Conditional DTE encodes a message according to a condition. In other words, it contains a DTE for each condition. We directly use IS-DTE to construct our IS-CDTE. Then our proposed IS-PMTE encodes M as follows. First, pass all generate sequence and choose one with its probability. Let's see the right figure. Password has two generating sequences with different probability. We take the second as an example. They encode each rule in the sequence by using IS-CDTE on the condition of previous rules. Because PCFG model, the condition probability does not depend on the condition. Then the two rules W goes to path and W goes to word use the same table for encoding. Finally, we concatenate these seeds, pass the concatenation to a fixed length, and output it.
Let's encourage people to go to the paper for the final conclusions. Do you have perhaps an email address on the concluding slide?
Yeah. I will conclude it. In summary, we solved how to design a PMTE for a probability model, but a secure PMTE still needs an accurate probability model to characterize the message distribution. This usually needs professional knowledge of the message distribution. We leave it to experts in related fields for future work.